Hello everyone, today we're going to be talking about advanced Boolean logic and bitwise operators. Specifically, we're going to go more in depth into this topic and show you a couple of applications where these things are really useful. So before we really start going into the advanced topics, we're going to do a really quick review, just a really quick overview of the things that were covered in last week's video about Boolean logic and bitwise operators. However, it will be a really quick overview. I'm not going to be teaching you anything. I'm just going to be reminding you of the important stuff. If you're having any lingering doubts or questions, I highly suggest you watch the video we did about Boolean logic and bitwise operators. It was published last week, and it goes really in depth into all the operators and how they react with the operands and just how they work in general. However, if you continue watching this video, I will assume you have a really good grasp on Boolean logic and bitwise operators, and the next few slides are just going to be a really quick review. So first up, we have the binary AND operator. Now, the binary AND operator, all it does is that it takes the logical AND between two operands, right? Now, this is the truth table for a binary AND. It only generates a 1 if both inputs are 1. Otherwise, they're all zeros. Again, this was covered in great detail in last week's video titled Binary Logic and Bitwise Operators. I won't be explaining how this works, where it comes from, the symbols, anything like that. That's all explained in last week's video. But this is a truth table. You can just think of it as AND. Both of these things need to be true for the whole sentence to be true. That's how the AND operation kind of works. Now on screen you can see the binary OR operator. The operator just takes the logical OR between two operands, and on screen you can see the truth table for this. You only generate a 1 if at least one of the inputs is a 1, or both of the inputs. You only really generate a 0 if both inputs are 0. So next up we have the XOR operator, or the exclusive OR operator. This one's similar to the OR operator, except that it will only generate a 1 if only one of the inputs is a 1. It'll generate a 0 if both are 0 or if both are 1. That's where the exclusive comes from. Only if one, specifically one of the inputs is a 1. Not 2, not 0. Just 1. And last but not least, we have the binary NOT operator, or the inverting operator. All it does is it inverts the bit. So if you give it a 0, it spits out a 1. If you give it a 1, it spits out a 0. There's a little bit of nuance when it comes to this operator in Python that Tyler goes into great detail and explains very well in last week's video. But when we're talking about this operator specifically, all it does is that it gives you the opposite. You give it a 0, it gives you back a 1. You give it a 1, it gives you back a 0. So far when using binaries in Python, what we've been doing is we've been using the bin function to convert a number to a binary representation. The problem with the bin function is that it doesn't actually return a number. It returns a string that holds the binary representation of the value you gave it, and it's completely accurate, but it's not very useful for computation. You know, I can't divide a string. I have to parse it out or convert it to a number. So it's not really very useful. However, Python allows us to make binary literals. When I say literal, I mean like that's the value. It's a specific value. So whenever you type a 5 in Python, like if you're doing a equals 5, that 5 is a literal. So if we wanted to put in a binary number inside of a variable as a literal, all we have to do is type 0b in front of it. That allows us to use a binary literal. So if you can see on screen right now, you can see the example line that says my binary equals 0b10001. So what's going to happen is that value is going to be read as a binary and then stored in my binary. Now when you use the variable later on, it's going to convert it to decimal for you, but it really doesn't matter. That's just a representation. The important part is that when we are handling it, when we're giving it to the variable, we're giving it in the accurate binary representation. That binary number is equal to, let me see, 1, 2, 4, 8, 16, 17, I believe, right? Let me confirm. 1, 2, 4, 8, 16. Yeah, 17. So that's equal to 17. So later on, if I were to go print my binary, it's going to print it out as 17, but that's fine because 17 and 10001 are the same exact thing. But being able to use these binary literals is going to come very handy when we start doing these advanced topics and these applications. So let me show you in Visual Studio Code what using this binary literal looks like, so you guys have a better idea going forward how to make sure that you are putting in a binary number in a variable and not worrying about whether it's a string or whether it's something else, so that it's something that you could do computation with. Alright, so I have Visual Studio Code opened up today. That's what I'm going to be using. It's what I prefer. But again, as I've said many times before, you can use whatever development environment is more comfortable for you. You can use Ripple, you can use Idle itself, you can use whatever you want. So if we want to use the binary literals, what we have to do, we have to make a variable, right? We have to do, let's call it my binary. And to use these binary literals, all you have to do is just type 0b and then the binary number. However, now we can't put actual like non-binary numbers. 2 is not a binary number, so we can't do it. Now, Visual Studio Code is very helpful. It's yelling at me saying, hey, you can't do that. What are you doing? Binary numbers are 0 and 1. What's a 2? It starts freaking out, and it's yelling at me that I can't do that. Other development environments may tell you, may not, but you should know that if you're typing 0b, anything after must be a valid binary representation. So if I do 0, 1, 0, 1, that's a perfectly valid binary representation, and that works. Now if I were to go print out my binary, here's something interesting. So if we were to do that, we get a 5, which sounds wrong, but is right, because 101 is 5, right? This is 1's place, this is the 2, this is 4, this is 4, and so we have a 1 in the 4 and in the 1, so we add those together, that's 5, so that is 5. And let me show you what 5 looks like. 5 looks like just the thing we gave it. But remember, bin gives you a string, so it's not that useful if you want to do computation. So after we assign the variable with this binary literal, Python says 101, bet that's a 5, let me save it, that's all I need. So it is just a 5. Now when we ask for it back, it's not really going to care that we gave it to it in a binary expression. It's just going to give us a 5 because it thinks, yes, a human, they only really care about regular decimal numbers, so let me give it to them in a 5. But again, remember, a 5 and 101 are the exact same thing. And now we can do a bunch of interesting stuff with this. We could do something like, so now that we know that's a 5, we can add a 1 to it here, and that should work. Let's see. Yeah, it does. So it added 1 to it. We can add a 5 to it too, and it'll be a 10. Yeah, see, and it works just fine. Because Python, the computer, doesn't care about how they're represented. It all looks the same to the computer. It's all 0s and 1s. So here we have it in 0s and 1s for the computer. They don't have to do anything at that point, and when they get to the 5, they immediately look at it as the 0 and 1s that it normally looks at it. And then when it gives it back to us, it converts it to decimal for our sake. But this is just a very easy way that you can ensure you can add binary numbers to your variables and make sure they're interpreted in the right way. Because now, like I said, we could do computation with this. Earlier when we did the bin function, it was a string. You can't really do anything useful with a string unless you start parsing it out, right? But since we're giving it to the variable in a binary literal, it's an actual value. It's a number. We could find out if it's even or odd. We can multiply it easily. We could add. We could just do all the stuff we can do to regular numbers. We can do to binary numbers now because we know how to do these binary literals. So now that we got all the basics out of the way, we can actually get into the advanced discussions and applications portion of this lecture. Again, after this point, I'm assuming you are very familiar with last week's video and everything discussed up to this point. If something's not making sense, please stop now, rewatch last week's video about binary logic and bitwise operators, rewatch the first portion of this video. But if you are watching the video after this point, I'm assuming you are very comfortable with these topics. So a really common problem that you try to do in just programming in general, is determining if a number is even or odd. Now to the right I have a table with the first, 7 or so even numbers, when you count up, along with their binary representation next to it. So if you look, they all have one thing in common. The rightmost bit is always 0. No matter what, it's always 0. Now, does this hold? Like, do all even numbers have this? Do all odd numbers have something else? Well, if we look, odd numbers always end in a 1, and all even numbers always end in a 0. The reason for this is that the rightmost bit adds a 1 to the number. If you add a 1 to an even number, you always end up with an odd number. That's just how it goes. Every other bit in a binary number would add an even number, and except the rightmost one, which would add a 1. So an even plus a 1 is always an odd. So a very, very easy way to identify if a number is even or odd is just to look at that rightmost digit. That's all you would have to do. Just look at it and identify whether it's a 1 or whether it's a 0. And that is a very quick and computationally cheap way of determining if a number is even or odd. So let's code it up so you guys can see exactly how that looks like. Okay, so now let's start by just writing a function that returns true or false depending on whether a number is even or not. So let's just call it is even, and we're going to give it n as the parameter. Now, traditionally, the way we would do this is we would just do if n is divisible by 2. That's what this means. That means that it's even, right? So we return true. Otherwise, if it's not true, we return false. So again, a number is even if it's divisible by 2. And all this is saying that if we divide n by 2 and there's no remainder, then we return true, which is just the same thing as saying n is divisible by 2, which is the same thing as saying n is even. So that's the way we've traditionally been doing this. Let's call this traditional even detection. Let's do that, and now let's run it. Let's make sure it's working. So let's do print is even. Let's do 0. Let's do 1. We know that should return a false. Let's see if it does. Let me go up. Python 3 test.py. We get false. Let's do 2 now. We get true. Now let's do a nice for loop for x in range from 0 to 10. Let's do that, and then let's change this a little bit. Let's say str x plus is even. Yeah, even question mark. str. Let's add another one here, and then let's add this here. This should cover all of them. And yeah, let's see if that works out. Oh, this should be x. So now if we do that, we get 0 is even. Okay, 2 is even. We get everything we expect, right? But that's the way we do it traditionally. Let's see how we would do it in a binary logic bitwise way. So let's do is even bitwise. Let's also give it n. And then all we're gonna do is we're gonna do this. We're gonna do last bit is equal to n bitwise and then binary 1. So remember, binary 1 is just a 1 all the way to the right. Everything else is 0. If the last bit is 1 and we AND it, then that means the last bit will be a 1. If the last bit is a 0 and we try to AND a 1 with it, it'll be a 0. So last bit will only be 1 if the last bit of n is 1. That's the only case it'll be that way. So now what we could do, we just do if last bit equals 1, then we know that it must be true, so we return true. Else, we return false. So now let's try that, but with this one. Oh, actually, I need to redo this part, because if the last bit is 1, that means it isn't even. It's odd, so we have to reverse this. Let me comment that. So if last bit is 1, then it is odd, so that we understand what's going on there. So let's run it now, and it works just the exact same way. If anything, this one's slightly better. Now, I believe we can do this and it'll still work. Let me check. Yeah, so the reason this works is that when you do an if statement, a true and a 1 are the exact same thing pretty much, and a 0 and a false are the exact same thing. So we could even make this simpler by just doing this, because last bit will be 1 if it's odd. This will only run if the thing inside is true. True and 1 are the same thing to the computer. So if it's 1, then it's true, so it's odd, so we print out false. If it's not 1, it has to be 0. And if it's 0, then that means not odd, so it is even, so we print out true. Now this is very computationally cheap. This is much faster to run. It is much easier for the computer to perform than this, because this has to do division, and division ain't that easy for a computer, and it has to also keep track of the remainder. It has to do a bunch of different things. Here we're just looking at the last bit, grabbing it, and then whatever it is, we do that. Technically, this could be condensed even more. For example, we could have gotten rid of that variable entirely and just done this. It would have worked just the same, and that's even less computationally expensive. This is the type of stuff you have to do if you really want to get the max performance out of your program, and if you want to have as low overhead as possible. Now, this isn't as nice for humans as just having this, because this just makes more sense, right? And I would comment this, say, getting rightmost bit of n. That's all that's doing. But being able to do a lot of bitwise stuff allows you to make really, really fast code, because it has such little overhead involved. And yeah, let's make sure this works again. Yep, it's working. 0, 2, 4, 6, 8. Perfect. It's working perfectly. Another really good application for bitwise operators is for flags. So we can use bitwise operators to keep track of the state of something. And normally we use a bunch of Boolean variables to do this. For example, if you had a car and you want to keep track whether it's running or not, whether the fuel is low, you can just have a couple Booleans that do that, called, is running. It's true if it is, it's false if it's not. You have another Boolean called is low fuel. It's true if there's low fuel, it's false if there isn't. It's not low fuel if you have a lot. You could definitely do that and just have a bunch of different Booleans, but you can also just have a single variable and use bitwise operators to just do the exact same thing. So yeah, like I was just saying, we may be interested in keeping track of these things. If a car is running, if it's in motion, if the AC is running, if the fuel's low, and again, I want you to think how you would do this. Again, one of the ways you could do them is just by doing Boolean variables, but is there any other way you could do it? I want you to think real quick how you would do it. So up to this point, this is how we would have normally done it. We would have had 4 Boolean variables, and we would have started them with, whatever status we wanted them to start off with. For example, if we have this status, if the AC is on, fuel's not low, the vehicle is on, and we're actually moving, that we would set it up like this. The problem with this is that we need 4 Boolean variables. And even though a Boolean can only have 1 or 2 values, in Python, a Boolean has a lot of overhead associated with it. So it actually takes up several, a significant amount of memory. Now, of course, having an extra Boolean ain't gonna, destroy your computer or anything like that, but it adds up in your program. It adds to the space requirements, the memory requirements, and it can affect runtime. So if there's an alternative to not have a bunch of different variables, we should take it. So instead of using several Boolean variables, we could just use a single integer variable. This would let us save space, because a single integer variable can take up less space than a bunch of Booleans in Python, because an integer can be many, many bytes long, so you can store a lot of bit values in there and only take up one variable. But again, how specifically would we do that? So you would have to use something called bitmask. Now, bitmask, they're just a concept in computer science that we came up with for a tool that we use. We use them to identify and turn off/off certain bits in a value. They're extremely useful for bitwise operation and for checking what the value of a specific bit is in a variable. They're usually all uppercase. They don't have to be that, but they tend to be, and they will have a 1 as one of their values. So you need to use binary literal in order to use these things, and you just have to set a 1 in the field. So here we have a table that shows a couple of masks called bit 0, which is the rightmost bit, bit 1, which is the second most most bit, and bit 2, which is the one right to the left of that, and bit 3, which is the leftmost binary bit. Now, they don't just have to have a single 1 in them. It can have multiple ones. You can add your own meaning to them, but this is as small as you can go. The good thing is that if we define these masks, we don't have to type 0b0001 every time we want to refer to that bit. We just type bit 0. We kind of just use them as a shorthand. And these bit masks will allow us to do a bunch of cool stuff to that bit location in a value. So if we apply this bit mask strategy to our car status problem, we could end up with these bit masks. We can have one called engine running, which corresponds to the rightmost bit. We can have one called car moving, which corresponds to the one just next to that one. AC running and fuel low for the next two. So we have masks for each status we want to keep track of. And if we have these 4 masks, we're getting started to really be able to solve this problem. However, we're going to need a couple of operations. We need to be able to do specific things to these specific bits if we want to be able to actually use integers as kind of like Booleans. So we need to be able to set a bit. When you set a bit, all you're doing is you're setting a specific bit to 1. Whether it was 0, whether it was 1, whatever value it was before, when you set a bit, it is now a 1. Then you have clear bit, which is the opposite. No matter what value was in there, you have a 0 now. When you clear a bit, you just reset the value of a specific bit to a 0. When you toggle a bit, you're switching the value. If it was a 0, it becomes a 1. If it's a 1, it becomes a 0. It kind of inverts it. And then you can check, and then we want to be able to check a bit. And when you check a bit, you just check if the bit is a 1. That's all you do. These are the operations that we need to know in order to be able to do to work with bitwise operators, in order to keep track of state, in order to use them as flags, so to speak. Alright, so first off, you have to talk about how to set up a bit. The way you set up a bit is just by doing that operation. You do value is equal to value bitwise or the bit mask you want to use. What this will do is that it will take value and it will set the bit at the bit mask location to 1 while not touching anything else. Because maybe there's stuff in value that we want to keep as a 0, as a 1, we don't want to touch. What this will do will mean that only the bit that we're interested in is set to a 1. Now, you can instead write value logical OR equals bit mask. You could do that. Those are the exact same thing. That's a shorthand for it. I prefer using the top one because it's a bit more clear, but the bottom one is just as equivalent. It does the exact same thing. The next operation we need to look at is how to clear a bit. And to clear a bit, you just do the operation on screen right now. You do value is gets value bitwise and then an inverted bit mask. What this will do is that it will set whatever bit mask represents to 0 while keeping everything else as it was. It won't mess with anything else except the thing that bit mask is pointing to. And again, you can still use the same shorthand that we saw for set a bit. It's at the bottom of the screen, but again, I prefer the top one because it just makes more sense to me. But they're completely equivalent, and feel free to use whichever one, makes more sense to you. So then the next operation we need to consider is how to toggle a bit. And again, when you toggle a bit, all you're doing is you're inverting the value there. So if you toggle a 1, it becomes a 0, and if you toggle a 0, it becomes a 1. And we do that using the exclusive OR operator. And again, as I've said the last two times, there's a shorthand for this. I don't prefer it, but it works just as good. I, in fact, encourage you to use the shorthand because it looks a lot more elegant. But it's just for me, I always get a little bit confused as to what's going on, and I have to take a second to convert it in my head. But they're both equally good, and they'll get the same exact thing done. The computer does the exact same thing when it gets to these lines. And this is very useful when you want to quickly alter a specific bit to be its opposite. You don't want to have to check and figure out what it was before and then, set it to the opposite. This will do it all for you. If it's a 0, it's going to become a 1. If it's a 1, it's going to become a 0. This is a very, very useful operation. And then perhaps the most important operation is how to check a bit, because being able to check a bit is the point of this whole section of this lecture, because if we can check a specific bit, then that's how we're going to be eliminating the need to have all these Boolean variables ready to go. So to check if a specific bit is 1, all you have to do is you have to do value and it with the bit mask, and then check if the value is equal to the bit mask. What is happening here is that if the bit that the bit mask is referring to is equal to 1, then that left side of the operation of the statement will end up as a 1 at the bit mask location. And if we set that, if that ends up being equal to the bit mask, the original bit mask, then that means there was a 1. If it ends up being 0, then that means there wasn't a 1, there was a 0. So this will only be true if that bit mask location has a 1 in it. It'll be false if it has a 0 in it. Extremely useful. This can be used in if-else statements, loops, or any place where a conditional expression is able to be used. This is what gives all the previous operations power, because without this, the previous operations are useless. Like, you can't do anything with them if you can't check a specific bit. Alright, so now that we have all those tools and we know how to do all these operations, let's actually code up the car status program using the bitwise operators in a single integer variable. Alright, so now we have Visual Studio Code open up, and now we're ready to go. So let's, do the classic, hello world to make sure everything's running properly. And it is, so we are good to go. So normally, if we want to do the Boolean thing, the way we would do it is like this. Flags or /status variables. You do something like this. We would do is on, let's say the car is on, is running, is moving. We would do true, let's say the AC is off, is AC on, let's set that to false because it's cold, and then is fuel low, let's set that to false. This is normally how we would do this, but the problem is that this takes up 4 whole variables, and in Python, 4 variables adds up to a lot of memory. Now, if you're using Python, you probably don't care all that much about, low memory overhead, but it's still a good skill to have when you guys learn other languages, or just in general to keep your Python memory requirements as low as possible. So we can do this, and this will work. We could have if statements determining which one of these is what and all that stuff, but it's just not efficient if we can do this instead. So this is how we would do it normally. The Boolean method. But if we want to do the bitwise method, we can do this. So we're going to have to define our masks first. Mask definition. And like I said, those tend to be uppercase. So let's do engine running. And let's say that's going to be the rightmost digit. So let's just write all these. And then let's say vehicle moving. And then let's do that. Let me tab them so they're all aligned and they look really nice. Yep. Okay, so B, and that's going to be the next one over. And the next one up is AC running. And then that's going to be that. And then we could do, the next one's going to be low fuel. And then that's going to be that. So now, these are our masks. And now we need to define our our actual status variable. Singular, single variable. So now we do, we're going to call it status variable. And then we do, let's call it my car status. Let's start off at 0 for now. Now, let's say I want to start the vehicle and turn on the AC. So again, what we would do for that, we would do 2 sets. So let's do set engine running. Let's do that all uppercase. There we go. And my car status. And remember, you could just do this if you want. So let's do that in this video. I want you guys to, get good habits. So let's do that, and then let's print it before and let's print it after. So let's print the initial status of my car status. So let's do original my car status. Let's do that, and then we do plus str my car status. Perfect. And then we'll do it right afterwards as well. So let's do that, and if we run it, my car status 1. Perfect. Now let's also turn on the AC. And the way we do that, same thing, same exact thing. So we do AC running, and then we just replace engine running. This is the set operation, so we just have to change the operands. If we run it, so now we're getting a 5. The thing is, that's correct. That's completely right, because if we go up here, AC running is the 3rd from right to left bit, and engine running is the 1st one. So this one represents a decimal 1. This one represents a decimal 2. This one represents a decimal 4, and this one represents a decimal 8. If these 2 bits are on, then you add them together to get the number. So 4 plus 1, that's 5. And that's what we're getting here. But that's not very useful to us, because I can't tell which bits are on as quickly. Because, for example, you're not always just going to have 4 bits. Maybe you want to keep track of 20 different bits. So you would have a lot more, and that's not as easy to keep track of. For 4 bits, it's pretty straightforward. But for something much larger, it's definitely not. So what we could do is we could use that bin function that we used previously to make sure everything's printed in binary. And let's do that. Let's copy, paste this everywhere. And let's run it now. And now we're good to go. Now it's printing it in the manner which we expect. But again, remember, 101 in binary is the same thing as 5. This bin is converting it to a string, so it's easy for us to look at it. It's not doing any actual mathematical stuff, or it's not changing anything. It's just converting it to a binary as a string for us to see it. So now let's continue on. What if, we're driving and we want to start driving? Then we have to set car in motion, whatever one that one was called. That was called vehicle moving. So now I want to get moving, right? So let's do that. Let's add more useful print statements. Print turning on car. And now we do print turning on AC. And now let's do another print here that says moving car. Now let's send it out. So let's see what we get. Okay, so let me see. Did I change it? Yeah. Okay, so now here should be my car status there. So now it's 111, which makes sense because the rightmost digit says whether the engine's on or not. The next one over is whether the vehicle's moving or not, and then AC running is the next one over. The 4th one from right to left is whether fuel is low, and you don't write leading 0. So technically, low fuel is marked as a 0 right now. Now, what if we're driving for a while and let me change this to vehicle moving. All right. what if we drive for 100 miles, right? Let's say 100 miles later, and now the low fuel light is gonna turn on. So we're gonna have to do that. We have to set that low fuel light. So setting low fuel, I think, yeah. Setting low fuel light came on. And then if we run it, now they're all ones. Now, if we decide that we don't want to waste as much gas, we're going to turn off the AC. And the way we do that, we do clear or reset. So let's do that. Let's clear AC running. And again, the way we do that is very similar. But now instead we're going to do an AND here, and we're going to invert the bit mask. So let's write this, turning off AC. So let's see if that works. So before we run it, let's see what we expect. So with all of these, up to this point, all of them are on. And we're turning off AC running. AC running is going to be the third one from right to left. So we're going to expect this one to turn into a 0. Let's see if that actually happens. And it did. That's exactly what happened. Now let's say that once we manage to find a gas station, we actually fill up. So let's do a print statement that says that. Let's say I filled up the tank. So now we can toggle the fuel light indicator now. Instead of, we could just set it, but I want you guys to see how toggling looks like. So we can just do it's going to be very similar to that, but let's do toggle instead. So we just do this operation and fuel light toggled. Now remember, if you toggle, what ends up happening is that 0 goes to 1, 1 goes to 0. So let's see if that worked the way we expected it to. So now the fuel light bit mask is going to be, sorry about that, the fuel light bit mask is going to be flipped. At this point, it's a 1. So if we flip it, it's going to be a 0. And the low fuel light is the fourth one from right to left. So let's see what happens if we do that. Yeah, so it is 0. Now, just because you can't see it doesn't mean it's not there. If you can't see it, that means it's a leading 0, and you ignore leading zeros. That's why it's not printed. But it's definitely a 0 now. However, let's say that at this point we kind of lost track of what's happening. Like I can't really tell at this point if, you know, what's on, what's off just by looking at this. But the computer's really good at it. So let's make a little if statement that checks all this stuff for us. So what if we want to check if the car's even on? So let's do that. My car status, engine running. If this is true, then the engine is running. So let's do that. Engine is running. Now let's do another check for pretty much all the other ones. Now we're doing just if statements because we want them all to be checked. We don't want to stop checking after if we find a true one. We want to check every single one here. So if we do that, we're going to want to do, which one's the next one up? It's going to be vehicle moving. So let's do that, and then AC running, and then we're going to have the other one, which is low fuel. Now if we do that, we could do vehicle is moving, car is moving, and then we can do the AC running one, which is AC is on, and then we could do fuel is low. So let's do that. At this point, we only have 1, 1, which means the two rightmost bits have a 1 in them. So this means that engine is running and vehicle is moving. So let's see if that's what we get printed at the end. And yeah, that's what we got printed. So now we can in fact do some interesting stuff. Let's delete all this for now. Let's say what we want to do is that we want to set the car status like this. Let's say the vehicle is moving, but that's all it's doing. If the vehicle is moving, but the engine is not running, we're going to want to identify that, right? So let's do this. We could combine these. We could do if, let's open this up, my car status and vehicle moving equals. Oh, wait, these are actually incomplete. They worked out, but that's incomplete. These should be equal to this. Okay. These won't always work out as nicely. This was just an accident that they happened to work out. I forgot to do these, but that's no big deal. Let me copy paste them and show you that they actually work just fine like this too. So let me go back. Let me Control Z. All right, perfect. And now this is how you're supposed to do them. You're supposed to do the variable and it with the bitwise, the bit mask, and then equal to the bit mask. Let's see if it's working. We had engine is running, car is moving last time. So let's see if we get that again. And we do get that again. And it worked earlier, but that's not guaranteed to happen. It might always happen in Python, but in other languages, it does not always happen. So always make sure you do this equality right here. Because sometimes you're going to want to compare more than one bit. Maybe your bit mask contains more than one, because this is also a perfectly valid bit mask. Maybe you always want to check these two, right? And if that were to happen, then that wouldn't have worked. So you have to make sure that this is like this. This will work without this side if it's always a single bit that you're checking, but it's not good practice because sometimes you're going to be wanting to check more than one bit. So always have this. I apologize for that. Now let's go back and delete all this. All right. And now let me comment this out for now. And now let's say the vehicle is moving. Let's say that's going to stay. We're going to keep going with that one. Now, if the vehicle is moving and then the engine is not running, now what probably happened is that they parked in a hill and didn't put their parking brake on, right? So let's identify that. Let's do my car status and bitwise and vehicle moving equals vehicle moving, right? We have that. So let's put that in its own paren. So we do that first, because of PEMDAS, and the following thing has to be true. The engine running has to be false. So what we do is the opposite of that. So we do this, and then we do engine running, but now it's not true. It can't be true. If that's the case, let's close up the parens. Let me zoom out a little bit so I can see it a bit better. If that is true, then what we do, we say your car is moving, but the engine is off. Did you park in a hill? Let's do that. Let's see if this works out. Yeah, so that worked out. But now let's set up the my car status with the vehicle is the engine is running as well. So right now vehicle is moving and then engine is running. And the reason I didn't do the bitwise OR is that here we're initializing it. Here we're pretty much saying, all right, forget about everything, set the vehicle to moving. Then down here what we're saying is, all right, set the engine running, but leave everything else like it was. I don't want to override it. Just set engine running to 1. So let's see this. Let's see if it runs. So this time it didn't run, right? Because if you look at the if statement, this triggers as true, but this is going to end up being false because when we do the bitwise and with this operator, it's going to be 1, but then this is saying if the engine running if this operation is not equal to a 1 at this location, then it's true. But if it is set, then this will lead to a 1 at engine running. This will be equal to engine running if it's true. So since engine is running, then this will generate something equal to engine running. So this will not run because the whole thing is not true. But then you could do a bunch of other stuff for it, because what if the AC is running and that's all that's done, that's happening. If that's the case, let's comment this out for a second. let's do if the same thing. Let's say if the engine is not running, so let's keep the right side the same, and then on the left side, let's check if the AC is running. Because if the AC is running but the engine's not off, you're gonna kill your battery. So we should warn them. We should be like, hey, the AC is on. Your battery is going to run out if you don't turn on the car. Right? So let's, we want to give them a friendly warning. And, we get the message. But what if the car is in motion too? You left the AC on, the car is not running, and the car is moving. Well, now we expect to see both of them, and we do see both of them. Now, this is a very unfortunate situation, because this means they left the keys in the car, so the battery's on, the AC's running, and they forgot the parking brakes. This is a very unfortunate situation. Their vehicle's going to be crashed, and the battery's going to be dead. It would be very unfortunate to be this dude right now. So, let's add more. Let's add more if statements. So, what if the engine is running? What if the engine is running? If the engine is running, then none of these get caught. But maybe I want to have a message for this, because maybe if the engine's running and the AC is on, but the vehicle is not in motion, that probably means they're just trying to, maybe they're waiting for someone while they do their shopping. Maybe they're just, getting some AC in the car. Maybe they're just hanging out. We want to, give them a nice message. So let's do that. However, now we're going to have 3 conditions that we need to check. So AC is running, engine is definitely running, and vehicle's not moving. So let's copy this one up here. Let me press enter so it looks a bit nicer, and then change this to vehicle moving. So this one's checking to see if the AC's on. This one is checking to see that the engine's running, and this one's checking to see that the vehicle is not moving. If that's the case, we just say, hey, I see that the AC is on as well as the car. I also see you aren't moving. Are you relaxing? Question mark, happy face. So let's see. Right now, it should catch it. Well, actually, no, it shouldn't, because it is moving. So right now, what we expect is nothing. We expect it to go inside none of these. So let's see if that happens. And that's what happens. So if we take out the vehicle moving part, now we get stuck in this one, because AC is running, engine is running, and vehicle is definitely not moving. Also, you saw me do this earlier. This is a perfectly valid thing to do. You could just do this, and what this does is that it ORs them, and then that allows you to set more than one at a time. You can even do it the same down here. This is just to save time. You could just do one at a time, or you could set multiples of them, and that's perfectly valid. So we can do this, and we could add OR statements, because maybe I want to check if the battery's low. I mean, if the fuel level's low, or if the engine is running and the AC is on but the vehicle's not moving. You could also have OR statements. All of this stuff works very nicely with all the conditional statement stuff we learned. And this is just a very neat way that you can just eliminate having to use Booleans, because we just did all the stuff we previously needed Boolean variables for just by using a simple integer and just using bitwise operators on the individual bit fields, the bit locations. And that's pretty much it for this application, but this is very powerful. They do stuff like this in embedded systems. They do them in programs that have very little memory available to them, so they just use stuff like this. This is stuff that is real, that is used in the actual industry, and that is very relevant if you're interested in a career in CS. Very important that you guys are familiar with this. You may not have to use this in your day-to-day, but you should always be able to use it if you have to. So that's pretty much all I have for you guys today, but to conclude this lecture, the main takeaway is that Boolean logic and bitwise operators are extremely useful. They help us save space, and they simplify the code immensely in the term of variable count. because we're going to have a lot less variables to keep track of, and there's just less stuff that changes. You're only changing one variable when you're using an integer as your status flag and just using the bit mask to set and reset bits. They are very, very useful in Python, but they're even more useful in other languages, such as C. Bit masking and bitwise operators are extremely useful in C because C has very little overhead and is very popular in embedded systems. And again, this type of logic is used extremely frequently in embedded programming. So knowing this is very useful for Python as well as other languages. It'll be helpful if you want to go down into a more low-level programming language, and it'll still be helpful if you want to go even higher level, if you want to abstract it even more. So that was it for today's lesson. If you have any questions at all, make sure you message us or leave a comment. Tell us, if you have any suggestions. If you're still lost in something, feel free to rewatch the video, of course. It's completely normal and somewhat expected to be a bit confused after your first viewing. So please watch this video as many times as you have to, and drop us any questions in the comments or just send us a message if you're still having any issues. Again, this lecture is you're kind of required to have a very good understanding of bitwise operators. So if that is where your issues lie, please watch last week's video on Boolean logic and bitwise operators. That gives you the basics of them and tells you how they work and the general tools to be able to solve bitwise problems. If you try to watch this video with having a good understanding of them, of bitwise operators and Boolean logic, that may be one of the reasons you might be a bit confused. So I highly suggest that you make sure you have a good understanding of the bitwise operators and Boolean logic video from last week before trying to understand this video.